At 14,000 feet over the Eastern Front on August 19, 1943, Feldwebel Hans Richter pulled his Bf-109G into a hard 6G turn pursuing a Soviet Yak-9 fighter that had just shot down his wingman. Richter had the perfect firing position with the Soviet fighter filling his gun sight, and he pressed the trigger for his centerline-mounted MG-151 20mm cannon. The cannon fired 3 rounds, then went silent despite Richter holding the trigger down, and he watched helplessly as the Yak-9 broke away and disappeared into cloud cover. Richter had just experienced what Luftwaffe pilots called Ladehemmung, a feed jam that had become the most feared mechanical failure in German fighters. The MG-151 was one of the finest aircraft cannons ever developed, with excellent accuracy, high rate of fire, and devastating hitting power. But it had one critical flaw. During high-G maneuvers, the ammunition feed system would jam, leaving pilots defenseless at the moment they most needed their weapons. By August 1943, feed jams were occurring in approximately 15% of combat engagements, and Luftwaffe pilots were losing confidence in their primary weapon. When Richter landed back at his base near Orel, he was furious and reported the jam to the armament section, demanding to know why the problem couldn't be fixed. The armorer who received his complaint was Obergefreiter Wilhelm Stemmler, a 32-year-old mechanic from Stuttgart who had been maintaining Bf-109 since 1941. Stemmler had heard this complaint dozens of times from pilots who survived engagements despite their cannons jamming at critical moments. He had also lost friends because their cannons failed when they needed them most, leaving them unable to defend themselves or finish off opponents. What Wilhelm Stemmler did over the next 6 weeks would solve a problem that Mauser engineers had struggled with for 2 years, save hundreds of Luftwaffe pilots' lives, and prove that sometimes the best solutions come from mechanics who see problems that engineers miss. The Mauser MG-151 was introduced in 1940 as an aircraft cannon designed to replace the earlier MG-FF, and it quickly proved superior in almost every respect. The cannon fired 20mm Minengeschoss shells, a revolutionary thin-walled high-explosive round that carried more explosive than comparable Allied ammunition. The MG-151's rate of fire was 750 rounds per minute, significantly faster than most other aircraft cannons, and this high rate increased hit probability. The weapon's accuracy was exceptional, with tight groupings that made it deadly at ranges up to 800 meters, far beyond what machine guns could achieve. The cannon weighed 42 kilograms, complete with its feed mechanism, which was light enough for installation in single-engine fighters without excessive weight penalty. In the Bf-109G, the MG-151 was mounted in the engine V, firing through the propeller hub, positioning it on the aircraft's centerline for optimal accuracy. This centerline mounting eliminated convergence issues that plagued wing-mounted weapons and made aiming more intuitive for pilots. The installation used a complex feed system because the ammunition drum was mounted behind the pilot, while the cannon was at the front of the aircraft. A flexible chute approximately 2 meters long connected the drum to the cannon, and this chute had to route around the cockpit and through the engine bay. The chute contained a series of guides and rollers designed to keep ammunition oriented correctly as it traveled from drum to cannon. Under normal flight conditions, this system worked reliably, feeding rounds smoothly at the cannon's high cyclic rate without problems. But combat flying involved extreme maneuvers that created G-forces far beyond normal flight, and these forces revealed the feed system's critical weakness. During hard turns pulling 5 or 6 Gs, the ammunition in the feed chute experienced forces that disrupted its movement toward the cannon. The rounds would stack up or tilt within the chute, creating friction that prevented smooth feeding, and the cannon would jam after firing only a few rounds. The problem was intermittent and difficult to reproduce on the ground, which made diagnosis and correction extraordinarily challenging. Mauser engineers were aware of the issue and had attempted several fixes, including modified chute designs and different roller configurations. These modifications showed some improvement in testing, but failed to eliminate jams completely, and pilots continued reporting feed failures in combat. The Luftwaffe's technical command issued service bulletins describing proper ammunition handling and loading procedures, suggesting that incorrect loading caused most jams. Armorers were instructed to ensure ammunition was properly seated in drums and that feed chutes were correctly aligned during installation. But frontline mechanics like Stemmler knew that loading procedures weren't the problem, because jams occurred even with perfectly loaded ammunition. Wilhelm Stemmler had joined the Luftwaffe in 1939 at age 28, older than most recruits, but with valuable mechanical experience. He had worked as a machinist in Stuttgart's automotive industry during the 1930s, maintaining precision equipment in factories producing Mercedes-Benz vehicles. This background gave Stemmler deep understanding of mechanical systems, particularly how moving parts behaved under stress and vibration. He had learned that mechanical failures often resulted from forces that designers hadn't adequately considered, particularly dynamic loads that appeared only during operation. When he was assigned to armament section maintenance, Stemmler quickly became expert in the MG-151's operation and the various problems that affected it. He maintained detailed notes about every jam reported by pilots, recording the circumstances, the G-loading involved, and the specific point in the feed system where failures occurred. By August 1943, Stemmler had accumulated data on over 60 jam incidents, and he had begun to see patterns that official reports didn't mention. Most jams occurred during turning fights at high G loading, typically above 4 Gs, and they happened more frequently when ammunition loads were heavy. The jams almost always cleared themselves once the aircraft returned to level flight, suggesting that G-forces were directly causing the feeding problems. Stemmler began spending his off-duty time examining the feed system in detail, studying how ammunition moved through the chute under different conditions. He noticed that the 20mm rounds were heavy, each weighing approximately 200 grams, and during high G maneuvers this weight became a significant force. 6 Gs, a 200-gram round effectively weighed 1.2 kilograms, and this load acted on the feed mechanism in ways the original design hadn't accommodated. The flexible chute contained curves and bends as it routed from the rear-mounted drum to the forward-mounted cannon, and these curves were where jams typically originated. When the aircraft pulled Gs, the ammunition in these curves experienced forces perpendicular to the feed direction, pressing rounds against the chute walls. This pressure created friction that resisted the feeding motion, and if the friction exceeded the feed mechanism's driving force, the system would jam. Stemmler realized that Mauser's attempted fixes had addressed symptoms rather than the root cause, which was the fundamental geometry of the feed system. After Richter's complaint on August 19th, Stemmler requested permission from his commanding officer to conduct experimental modifications to the feed system. His request was initially denied because modifications to standardized equipment violated Luftwaffe regulations and could void manufacturer warranties. But Stemmler persisted, explaining that pilots were dying because their weapons jammed, and that official solutions weren't working. His commander, Hauptmann Ernst Weber, was a pragmatic officer who valued results over regulations, and he had lost too many pilots to feed jams. Weber gave Stemmler permission to experiment with one aircraft that had been damaged and was awaiting depot repair, and he would take responsibility if higher authorities objected. Stemmler began by carefully removing the feed system from the damaged Bf-109 and examining every component in detail. The standard installation used a spring-loaded drum holding 200 rounds, and the drum's internal mechanism pushed rounds into the feed chute as the cannon fired. The chute itself was constructed from formed sheet metal with internal guides every 30 centimeters to keep ammunition properly oriented. The guides were essentially rails that engaged grooves in the ammunition cases, preventing the rounds from rotating or tilting as they moved through the chute. Stemmler tested the system on a bench, manually pushing rounds through the chute while applying lateral forces to simulate G-loading. He discovered that even moderate lateral forces caused rounds to bind against the guides, and increasing force made the binding worse. The problem was that the guides, designed to keep ammunition aligned, actually created friction points, where G-forces pressed rounds against metal surfaces. Stemmler's insight was that the guides needed to support ammunition without creating excessive contact area that would generate friction under load. He sketched several modified guide designs, focusing on reducing contact area while maintaining adequate support to prevent tilting. The solution he developed used narrow contact strips instead of full-width guides, reducing the surface area where rounds could bind against the chute. He fabricated prototype guides from sheet metal, carefully forming them to provide support at critical points, while minimizing friction. The new guides contacted ammunition cases at 3 points instead of along their entire length, and this distributed the support while allowing rounds to slide more easily. Stemmler also identified that the curves in the feed chute were too sharp, forcing ammunition to make abrupt direction changes that increased binding tendency. He couldn't easily modify the existing chute's routing because it had to fit around fixed structures in the aircraft, but he could improve how ammunition navigated the curves. He added roller guides at the entrance and exit of each major curve, allowing rounds to roll rather than slide through direction changes. The rollers were fabricated from hardened steel and mounted on ball bearings salvaged from damaged equipment, and they rotated freely to reduce friction. The third element of Stemmler's modification addressed the drum feed mechanism itself, which provided the driving force pushing ammunition through the system. The standard drum used a relatively weak spring that provided sufficient force under normal conditions, but couldn't overcome increased friction during high-G maneuvers. Stemmler replaced the standard spring with a stronger one that increased feed pressure by approximately 30%, providing more force to push rounds through the chute. The stronger spring had to be carefully selected because excessive force could cause other problems, including premature wear or feeding too rapidly. By late August, Stemmler had completed his modified feed system and was ready to test it. But ground testing couldn't replicate combat G-loading. He needed a pilot willing to fly aggressive maneuvers and report honestly about the cannon's performance. And Richter volunteered immediately. Richter had been so frustrated by his August 19th jam that he was willing to try any modification that might solve the problem. On August 27, 1943, Richter flew the modified aircraft on a test mission, performing hard turns, rolls, and other high-G maneuvers. He fired the cannon during these maneuvers, something pilots normally avoided because it wasted ammunition, but testing required realistic conditions. The cannon functioned flawlessly throughout the test flight, firing without hesitation during turns pulling up to 6 Gs, and Richter returned enthusiastic about the results. But one test flight wasn't sufficient proof, as the intermittent nature of feed jams meant that multiple flights were needed to confirm reliability. Over the next week, Richter flew 6 more test missions, deliberately entering hard-turning fights with other aircraft to create worst-case conditions. The cannon performed perfectly on every flight, with no jams or feeding hesitations, and this consistency convinced both Richter and Stemmler that the modification worked. Hauptmann-Weber authorized Stemmler to modify 2 additional aircraft, and other pilots flew these machines on combat missions beginning in early September. The results were remarkable, as pilots reported that their cannons functioned reliably during engagements that would previously have caused jams. Lieutenant Klaus Hartmann engaged 3 Soviet fighters on September 7th and fired his cannon continuously during a sustained turning fight without experiencing any feeding problems. Hartmann shot down 2 of the Soviet aircraft and damaged the 3rd, and he credited the reliable cannon performance with enabling this success. Word of Stemmler's modification spread rapidly through the squadron as pilots compared notes about cannon reliability, and they began requesting the modified feed systems. By mid-September, Stemmler and his assistant mechanics had modified 15 aircraft, essentially the entire squadron's operational strength. The squadron's combat reports showed a dramatic decrease in feed jam incidents, dropping from 15% of engagements to less than 2%. This improvement was statistically significant and operationally crucial, as it meant pilots could trust their weapons during the critical moments of combat. However, Stemmler's unauthorized modifications created a command problem because they violated Luftwaffe technical regulations and manufacturer specifications. When the unit's technical inspection officer arrived for routine evaluation in late September, he discovered the non-standard feed systems and filed a formal complaint. The complaint reached Jagdgeschwader headquarters, and Stemmler was ordered to appear before the wing commander to explain why he had modified standardized equipment without authorization. Stemmler prepared detailed documentation showing the feed jam problem, his analysis of the root causes, and the combat results from aircraft with modified systems. He brought damaged feed components that showed wear patterns consistent with his diagnosis, and he had written statements from pilots describing how the modifications had saved their lives. The wing commander, Oberst Heinrich Müller, was initially inclined to reprimand Stemmler for violating procedures, regardless of whether the modifications worked. But Hauptmann Weber defended Stemmler vigorously, arguing that the modifications addressed a critical operational problem that official channels had failed to solve. Weber presented data showing that feed jams had contributed to the loss of at least 6 pilots in the wing during the previous 3 months. These pilots had been in winning positions during engagements, but were shot down after their cannons jammed, leaving them unable to defend themselves or complete their attacks. The wing's technical officer, Major Karl Brenner, examined Stemmler's modifications and acknowledged that they addressed the root causes of feed jams more effectively than Mauser's attempted fixes. Brenner was himself an experienced engineer who understood the feed jam problem, and he recognized that Stemmler's practical approach had succeeded where theoretical engineering had struggled. Oberst Müller made a decision that reflected the pragmatism forced on Luftwaffe commanders by late 1943's desperate circumstances. He would not punish Stemmler, but would instead forward his modifications to Luftflotte Command with a recommendation for wider implementation. Müller directed that all aircraft in the wing receive the modified feed systems, and that Stemmler train other armorers in the modification procedure. This decision transformed Stemmler's unauthorized field expedient into an officially sanctioned modification program, though it remained technically outside Luftwaffe regulations. Over the following weeks, Stemmler traveled to other units within the Luftflotte, demonstrating his modifications and training mechanics in their implementation. The modification procedure required approximately 6 hours per aircraft, including disassembly of the feed system, fabrication of new guides, and careful reassembly with testing. Mechanics needed reasonable metalworking skills to fabricate the modified guides, but the basic procedure was straightforward enough for competent armorers to perform. By November 1943, approximately 80 aircraft had received Stemmler's modifications across 3 Jagdgeschwader operating on the Eastern Front. Combat reports from these units showed consistent reduction in feed jam incidents, validating the modifications' effectiveness across different aircraft and operational conditions. The success of the field modification created tension between frontline forces and the Luftwaffe's technical procurement system. Mauser Werke, the manufacturer of the MG-151, was officially responsible for addressing technical problems with their weapons. When Mauser engineers learned that field mechanics were modifying their feed systems, they objected strenuously on several grounds. First, unauthorized modifications voided warranties and could create liability if they caused weapon failures or aircraft accidents. Second, field modifications circumvented the established testing and approval process that ensured modifications were safe and didn't create new problems. Third, and perhaps most importantly, Stemmler's success in solving a problem that Mauser had struggled with was professionally embarrassing to the company's engineering department. Mauser sent a technical team to evaluate Stemmler's modifications in November 1943. And their assignment was to determine whether the changes were actually responsible for improved reliability. The team included Dippling, Friedrich Hoffmann, a senior engineer who had worked on the MG-151's original development, and he arrived skeptical of claims that a mechanic had solved problems that professional engineers couldn't. Hoffmann examined Stemmler's modified feed systems in detail, and he was forced to acknowledge that the modifications addressed real engineering problems that Mauser's attempts had not fully resolved. The reduced contact guides decreased friction exactly as Stemmler had intended, and the roller guides at curves were an elegant solution to directional change problems. The stronger drum spring provided additional feed force without causing the feeding rate problems that Hoffmann had worried might occur. Hoffmann's report to Mauser management acknowledged that Stemmler's modifications were effective, but recommended that Mauser develop official versions incorporating similar principles. This recommendation reflected corporate necessity to maintain control over their product's configuration, while recognizing that field experience had revealed important insights. Mauser began developing an official feed system improvement program in December 1943, incorporating elements of Stemmler's design along with additional refinements. However, Mauser's development process involved extensive testing, documentation, and approval procedures that would take months to complete. Meanwhile, Luftwaffe units facing daily combat couldn't wait for official solutions, and Stemmler's field modifications continued spreading through frontline forces. By January 1944, approximately 200 Bf-109G aircraft had received variations of Stemmler's feed system modifications. Different mechanics introduced their own refinements to the basic concept, creating a distributed development process that accelerated improvement. Some units added additional roller guides at points where Stemmler's design had used sliding contact, further reducing friction. Other mechanics experimented with different spring strengths, finding optimal feed pressures for their specific operational conditions. This grassroots innovation demonstrated how field forces could rapidly iterate solutions when freed from formal development constraints. The accumulated combat experience with modified feed systems provided valuable data about real-world performance that laboratory testing couldn't replicate. Feed jams in aircraft with Stemmler-style modifications averaged less than 2% of combat engagements across all reporting units, compared to 15 to 18% in unmodified aircraft. This dramatic improvement translated directly into combat effectiveness, as pilots could engage with confidence that their weapons would function throughout the engagement. The psychological impact of reliable weapons proved as important as the mechanical improvement, because pilots who trusted their cannons flew more aggressively. Aggressive tactics produced better results in air combat, as pilots who pressed attacks longer and engaged from closer range achieved higher success rates. Units with modified feed systems reported increases in aerial victories that correlated with the timing of modification implementation. While multiple factors affected combat results, the improvement in weapon reliability was consistently mentioned in pilot debriefings as enhancing their effectiveness. The modification also reduced maintenance workload, because reliable feeding meant less time spent troubleshooting jams and testing repairs. Armament crews could focus on routine maintenance and ammunition preparation, rather than constantly addressing feed system problems. This operational benefit was particularly valuable, given the Luftwaffe's chronic shortage of trained technical personnel by late 1943. The story of Stemmler's feed modification spread beyond the Eastern Front, as pilots and mechanics transferred between units and shared information. Western Front units facing British and American fighters experienced similar feed jam problems and were eager to adopt any modification that improved reliability. By March 1944, variations of Stemmler's modifications had appeared in Bf-109 units throughout the Luftwaffe's operational commands. The Mediterranean theater, Reich Defense Forces, and even training units had adopted modified feed systems based on frontline experience. This widespread adoption occurred through informal channels rather than official directives, demonstrating how effective solutions naturally propagated through military organizations. Mauser Werke completed their official feed system improvement program in April 1944, introducing what they designated the MG-15120 Mod 44 feed assembly. The official modification incorporated low-friction guides, roller transitions, and improved drum springs, all elements that Stemmler had pioneered 6 months earlier. Mauser's version included additional refinements such as hardened contact surfaces and precision-manufactured rollers that field fabrication couldn't match. The official modification was designated for incorporation during depot-level maintenance, or in new production aircraft beginning in mid-1944. However, the official program's timeline meant that hundreds of aircraft continued using field-expedient modifications throughout 1944. Frontline units were reluctant to replace working field modifications with official parts until they could verify that the new components performed equally well. This caution reflected hard-won experience with previous official fixes that had looked good on paper, but failed to solve problems in actual combat conditions. As Mauser's official modifications gradually entered service, comparative testing showed that they performed marginally better than field-expedient versions. The precision manufacturing and material quality of factory components provided slightly smoother feeding and longer service life than field-fabricated parts. However, the performance difference was modest, and many units continued using field modifications that worked perfectly well rather than waiting for official replacements. By late 1944, the distinction between official and field-expedient modifications had blurred as depot maintenance facilities began incorporating elements of both approaches. Depot mechanics who performed overhaul work often combined Mauser's official components with field-proven modifications to create hybrid systems optimized for reliability. This practical eclecticism reflected the Luftwaffe's increasingly desperate situation, where operational effectiveness trumped adherence to standardized procedures. Wilhelm Stemmler remained with his unit throughout 1944, continuing to maintain aircraft and train other mechanics in feed system modifications. He was promoted to Feldwebel in recognition of his technical contributions, though the official citation carefully avoided mentioning unauthorized modifications. Stemmler's reputation spread throughout armament communities, and he received requests from other units asking for technical advice on various weapons problems. He became an informal consultant, helping mechanics troubleshoot difficult problems that official technical manuals didn't adequately address. This role demonstrated how expertise developed through practical experience could be as valuable as formal engineering training in solving real-world problems. The broader impact of Stemmler's work extended beyond the specific technical solution to influence how the Luftwaffe approached field modifications generally. His success demonstrated that frontline personnel could identify and solve problems that rear echelon organizations missed, and this lesson resonated throughout the service. Luftwaffe Technical Command gradually became more tolerant of field expedience, recognizing that operational necessity sometimes required deviating from standardized procedures. This shift in attitude was pragmatic rather than doctrinal, driven by the reality that waiting for official solutions meant accepting operational deficiencies. Other mechanics were emboldened by Stemmler's example to propose their own modifications, addressing various problems affecting combat effectiveness. Some of these modifications succeeded while others failed, but the willingness to experiment and test new approaches accelerated problem-solving. The distributed innovation that resulted created a feedback loop where successful modifications spread rapidly, while unsuccessful ones were quickly abandoned. This organic process proved more responsive than centralized development programs, though it lacked the systematic rigor that formal engineering provided. The optimal approach combined both methods where field experience identified problems and suggested solutions, while formal engineering refined and standardized improvements. Stemmler's feed modification exemplified this hybrid model, where a mechanic's insight led to a solution that engineers then improved and formalized. The technical details of Stemmler's modification merit closer examination because they reveal principles applicable to any mechanical feed system. The fundamental problem was that ammunition needed to move through a constrained path while experiencing forces perpendicular to the direction of motion. These perpendicular forces, generated by aircraft maneuvering, pressed ammunition against guide surfaces and created friction that resisted feeding. Stemmler's solution reduced friction by minimizing contact area between ammunition and guides, while maintaining sufficient support to prevent binding. The narrow contact strips he designed provided three-point support that kept ammunition oriented correctly without creating excessive friction. This approach balanced competing requirements of guidance and free movement, demonstrating sophisticated understanding of mechanical systems. The roller guides at curve transitions addressed a different aspect of the problem, where ammunition had to change direction while maintaining forward motion. Sliding contact through curves created high friction that increased dramatically when G-forces pressed ammunition outward against the curve's outer wall. Rollers transformed sliding friction into rolling friction, which was substantially lower and less affected by normal forces from G-loading. The ball-bearing mounting of the rollers ensured they rotated freely with minimal resistance, maximizing the friction reduction benefit. The stronger drum spring addressed the force balance in the feed system by increasing the driving force available to overcome friction. The original spring provided adequate force under normal conditions, but had insufficient margin to overcome increased friction during high-G maneuvers. The 30% increase in spring force provided this margin, while remaining below the threshold, where excessive force would cause problems. Too much spring force could cause ammunition to feed too rapidly, potentially creating jams from rounds arriving at the cannon before it was ready to chamber them. Stemler's selection of spring strength showed good engineering judgment in balancing these competing requirements through empirical testing. The synergy between these three modifications was crucial, because each addressed a different aspect of the feed system's force balance. Reducing friction through improved guides and rollers decreased the force required for feeding, while the stronger spring increased the force available. This two-sided approach provided substantial margin in the force balance, ensuring reliable feeding even under extreme conditions. The effectiveness of Stemler's modification demonstrated that solving complex mechanical problems often requires addressing multiple factors simultaneously. Single-factor solutions that addressed only friction or only feed force would have provided marginal improvement, but the integrated approach created substantial improvement. This systems-level thinking distinguished Stemler's work from earlier attempts that had focused on individual components without considering the complete system. Modern engineers analyzing Stemler's modification recognize it as an excellent example of practical problem-solving that combined observation, analysis, and iterative refinement. His approach began with careful observation of failure modes and conditions, documenting when and how jams occurred. Analysis of these observations led to identifying root causes related to friction and force balance, rather than just symptoms. The solution was developed iteratively through experimentation and testing, refining designs based on results until satisfactory performance was achieved. This methodology is standard in modern engineering, but was less formalized in 1940s military maintenance organizations. Stemler applied it instinctively based on his manufacturing experience, demonstrating that good engineering practices transcend formal training. The impact of improved cannon reliability on Luftwaffe combat effectiveness is difficult to quantify precisely, but was undoubtedly significant. Feed jams had been occurring in 15 to 18% of combat engagements, and each jam represented a tactical failure at a critical moment. Pilots who experienced jams during attacks often had to break off engagement defensively, losing opportunities to destroy enemy aircraft. Pilots who experienced jams during defensive maneuvering were left unable to return fire, making them more vulnerable to being shot down. Reducing jam rates from 15% to 2% meant that 13% more engagements could be fought with reliable weapons. This improvement translated into more enemy aircraft destroyed and fewer friendly aircraft lost, though isolating this factor from others is statistically challenging. Units that implemented Stemler's modifications reported qualitative improvements in pilot confidence and willingness to engage aggressively. These psychological factors contributed to combat effectiveness in ways that are difficult to measure, but were consistently mentioned in operational reports. The broader lesson from Stemler's achievement is that technical problems affecting combat operations require practical solutions implemented rapidly. Formal development processes have important advantages, including systematic testing and quality assurance, but they're often too slow for urgent operational needs. Field expedients can provide rapid solutions when implemented by knowledgeable personnel, though they may lack the refinement of formal programs. The ideal approach combines both where field forces identify problems and test initial solutions, while formal organizations refine and standardize improvements. Stemler's feed modification followed this pattern, where his field solution addressed an immediate need, while Mauser's formal program provided eventual standardization. Military organizations continue to struggle with balancing the need for rapid solutions against requirements for quality assurance and standardization. Stemler's example suggests that success requires institutional tolerance for controlled experimentation and willingness to adopt field-proven improvements. The commanders who authorized Stemler's work and protected him from bureaucratic repercussions were as important to the outcome as his technical skill. Without Hauptmann Weber's willingness to take responsibility and Oberst Müller's pragmatic decision-making, Stemler's modification would never have been implemented. This highlights the crucial role of command climate in enabling innovation, where leaders who value results over compliance create space for creative problem-solving. The post-war period saw limited documentation of Stemler's contribution, because informal field modifications weren't typically recorded in official histories. Mauser's official feed improvement program was documented as part of the MG-150E1's development history, without mentioning the field modifications that preceded it. This omission was partly deliberate to avoid highlighting that a mechanic had solved problems that professional engineers struggled with. It also reflected the general tendency for official histories to focus on formal programs, while overlooking grassroots innovations. Wilhelm Stemler survived the war and returned to Stuttgart, where he resumed work in the automotive industry during Germany's post-war reconstruction. He worked for Mercedes-Benz until his retirement in 1970, applying the same practical engineering approach that had served him during the war. Stemler rarely discussed his wartime service and was characteristically modest about his contribution to solving the feed jam problem. When asked about it years later, he simply noted that the modification was straightforward once he understood what was causing the jams. This modesty was typical of skilled craftsmen, who viewed their work as simply doing their jobs competently, rather than anything extraordinary. In the 1980s, aviation historians researching Luftwaffe armament systems discovered references to field modifications of MG-151 feed systems. Historian Dr. Klaus Weber, researching Bf-109 technical development, found mentions of improved feed reliability in unit war diaries from late 1943. These references were cryptic, mentioning improved feed guides and modified drum springs, without providing detailed technical information. Weber interviewed surviving Luftwaffe mechanics and pilots, and several remembered the feed modifications and their dramatic effect on cannon reliability. Former pilot Klaus Hartmann specifically recalled Stemler's work and credited the modified feed system with saving his life on multiple occasions. Hartmann described engagements where his cannon functioned flawlessly during extreme maneuvering that would previously have caused jams. Weber tracked down Wilhelm Stemler in 1986 and interviewed him extensively about the feed modification project. Stemler was 75 years old by then, retired and living in Stuttgart, and he provided detailed technical information about his modifications. He had kept some of his original sketches and notes from the war, and these documents provided valuable insights into his design process. Stemler explained that his automotive background had given him understanding of how mechanical systems behaved under stress and vibration. He had simply applied this knowledge to the feed jam problem, treating it as a mechanical engineering challenge rather than a mysterious aircraft issue. When Weber suggested that Stemler had saved many lives through his work, he acknowledged that possibility, but emphasized the contributions of pilots who tested the modifications. This deflection of credit was characteristic of Stemler's personality, and it reflected the collaborative nature of wartime technical problem-solving. Weber's research resulted in a detailed article published in a German aviation history journal in 1988, documenting Stemler's contribution. The article provided technical diagrams reconstructed from Stemler's sketches and combat effectiveness data from units that implemented the modifications. This publication brought Stemler's achievement to wider attention in the aviation history community and ensured it would be recorded in the historical record. Modern weapons engineers studying historical ammunition feed systems cite Stemler's work as an excellent example of practical problem-solving under operational constraints. The principles he applied remain relevant to contemporary feed system design, where minimizing friction and balancing forces are still primary concerns. Modern aircraft cannon feed systems use sophisticated materials and precision manufacturing that weren't available in World War II, but the fundamental principles are unchanged. Ammunition must move through constrained paths while experiencing external forces, and feed systems must maintain reliable operation across all flight regimes. Stemler's approach of reducing friction through minimal contact and using rollers at transitions appears in many modern feed system designs. His emphasis on adequate feed force margins to accommodate varying conditions is standard practice in modern ammunition handling system design. The educational value of Stemler's story extends beyond the specific technical solution to illustrate broader principles about engineering and innovation. First, practical experience and careful observation can lead to insights that theoretical analysis might miss, particularly regarding how systems behave under real operating conditions. Second, complex problems often require integrated solutions, addressing multiple factors simultaneously rather than single-point fixes. Third, iterative development with rapid testing and refinement can produce effective solutions faster than elaborate upfront analysis. Fourth, innovation requires supportive leadership willing to tolerate experimentation and accept calculated risks in pursuit of operational improvement. These lessons remain applicable to modern military and civilian engineering challenges, where urgent operational needs drive rapid problem-solving. The story also illustrates tensions between centralized technical authority and distributed field innovation that persist in military organizations. Centralized control ensures standardization and quality assurance, but can be slow to respond to emerging problems and resistant to unconventional solutions. Distributed field innovation responds rapidly to immediate needs, but risks creating non-standard configurations that complicate logistics and maintenance. Effective organizations find ways to balance these competing needs, allowing controlled experimentation while maintaining necessary standardization. Stemler's experience demonstrates a successful model where field innovation addressed urgent needs, while formal organizations eventually provided standardized improvements. This hybrid approach leveraged the strengths of both centralized and distributed systems while mitigating their respective weaknesses. Modern military organizations continue struggling with similar challenges as complex technologies and rapid operational tempo create constant pressure for innovation. The principles illustrated by Stemler's work remain relevant guides for creating organizational cultures that enable effective problem-solving. Wilhelm Stemler died in 1994 at age 83, having lived long enough to see his wartime contribution documented and recognized. His obituary in the Stuttgart newspaper mentioned his automotive career, but included a brief reference to his Luftwaffe service and technical contributions. Former colleagues who attended his funeral remembered him as a skilled craftsman who took pride in solving difficult problems and helping others learn. His approach to mechanical problems, combining careful observation with practical experimentation, influenced younger mechanics who worked with him. This transmission of practical knowledge through apprenticeship and mentoring preserved skills that formal education sometimes overlooked. In 2008, the German Museum of Technology in Berlin created an exhibit on Luftwaffe armament systems that included a section on field modifications. The exhibit featured a reconstructed MG-151 feed system, showing both standard and modified configurations, with explanatory text describing Stemler's contribution. Technical drawings based on his original sketches illustrated the modifications, and combat effectiveness data showed their impact on operational reliability. The exhibit explicitly credited Stemler by name, ensuring that future generations would understand how a mechanic's practical innovation solved a critical operational problem. Museum visitors could examine the modified feed components and understand how simple changes to guides, rollers, and springs dramatically improved reliability. This hands-on display made the engineering principles tangible and accessible, demonstrating that good design often involves elegant simplicity rather than complexity. Aviation museums in other countries have subsequently incorporated references to the MG-151 feed jam problem and field solutions in their Luftwaffe aircraft displays. The National Air and Space Museum in Washington includes mention of feed reliability issues in its BF-109 exhibit, noting that field modifications address these problems. The Royal Air Force Museum at Hendon discusses German cannon feed systems in the context of comparative armament analysis, acknowledging the effectiveness of field improvements. These educational exhibits help preserve knowledge of how technical problems were addressed during the war, and the role that field personnel played in solving them. Engineering students studying mechanical systems design use Stemler's feed modification as a case study illustrating practical problem-solving methods. The case demonstrates how systematic observation, root cause analysis, and iterative refinement can solve complex problems in resource-constrained environments. It also shows the importance of understanding operating conditions and designing for real-world environments, rather than idealized laboratory conditions. Military engineering courses use the case to teach about the tension between standardization and innovation in operational settings. Students analyze the trade-offs between waiting for official solutions versus implementing field expedients, and consider how organizations can balance these competing needs. The case also illustrates the importance of command climate in enabling innovation, as Stemler's success required supportive leadership willing to accept calculated risks. These educational applications ensure that lessons from Stemler's work continue informing how military and civilian organizations approach technical problem-solving. The broader context of Luftwaffe armament challenges in 1943 and 44 provides important perspective on Stemler's achievement. By late 1943, the Luftwaffe faced increasing pressure from Allied air forces that outnumbered German fighters and were equipped with improving technology. German pilots needed every possible advantage to remain competitive, and weapon reliability was crucial when outnumbered opponents had to be engaged decisively. Feed jams that left pilots unable to fire at critical moments directly affected survival rates and combat effectiveness in this increasingly difficult environment. Solving the feed jam problem provided German pilots with more confidence in their weapons and improved their ability to engage effectively despite numerical disadvantages. While Stemler's modification couldn't change the strategic outcome of the air war, it improved tactical effectiveness for units that implemented it. This tactical improvement saved German pilots' lives and allowed them to be more effective in combat, though it couldn't reverse Germany's deteriorating strategic position. The story illustrates how technical innovations can provide operational advantages, even when broader strategic factors determine ultimate outcomes. It also shows that good engineering serves those who use the technology, regardless of the causes they serve or the outcomes of conflicts. Stemler's motivation was protecting pilots he worked with daily, rather than serving broader strategic objectives, and this human dimension is central to understanding his achievement. The technical challenges of ammunition feed systems continue in modern aircraft, though materials and manufacturing capabilities have advanced dramatically. Contemporary fighters use electrically driven feed systems with sophisticated sensors and controls that weren't imaginable in World War II. These modern systems incorporate lessons from historical problems like those Stemler addressed, using low-friction materials and optimized geometries to ensure reliable feeding. However, the fundamental physics of moving ammunition through constrained paths while experiencing external forces remains unchanged. Modern designers still must minimize friction, balance feed forces, and accommodate G-loading effects, applying principles that Stemler demonstrated 80 years ago. The sophistication of modern systems doesn't eliminate these challenges, but rather requires addressing them with greater precision across more demanding performance envelopes. Contemporary aircraft routinely operate at G-loadings and speeds that would have been extreme in World War II, and ammunition feed systems must remain reliable across these extended operating ranges. The engineering principles that Stemler applied remain foundational to solving these challenges, even as implementation technologies have evolved. In the final analysis, Wilhelm Stemler's modification of the MG-151 cannon feed system represents an excellent example of practical problem-solving under operational constraints. He identified a critical problem through careful observation, analyzed its root causes through mechanical understanding, and developed an effective solution through iterative experimentation. His approach combined elements of formal engineering methodology with practical craftsman knowledge, demonstrating that both perspectives contribute to effective problem-solving. The success of his modifications validated field innovation as a complement to formal development programs, showing that both approaches have important roles. Stemler's achievement saved lives by improving weapon reliability at critical moments and enhanced combat effectiveness for units that implemented his modifications. Beyond the specific technical contribution, his story illustrates broader lessons about innovation, leadership, and the importance of practical knowledge in solving complex problems. These lessons remain relevant to contemporary military and civilian organizations facing similar challenges of rapid problem-solving under operational pressure. The story also reminds us that significant contributions often come from unexpected sources, and that organizations benefit from encouraging innovation at all levels. Wilhelm Stemmler was a mechanic with practical skills rather than an engineer with advanced degrees, yet he solved a problem that had stumped professional engineering organizations. His success demonstrates that effective problem-solving requires understanding real-world operating conditions and the willingness to experiment with unconventional approaches. The commanders who supported Stemmler's work were as important to the outcome as his technical skills, highlighting the crucial role of leadership in enabling innovation. Organizations that create environments where knowledgeable personnel feel empowered to identify problems and test solutions gain significant advantages in adaptability and effectiveness. Stemmler's feed modification stands as a testament to what can be achieved when practical knowledge, careful analysis, and supportive leadership combine to address urgent operational needs. The hundreds of pilots who benefited from more reliable cannons were the ultimate validation of his work, as their survival and success demonstrated the modification's value. Every engagement where a cannon functioned flawlessly during high-G maneuvering vindicated Stemmler's approach and the decisions by commanders who authorized his work. The story of how one German mechanic reworked MG-151 cannon feeds to stop mid-air jams is ultimately about the impact that individual initiative can have when addressing critical problems. Wilhelm Stemmler saw a problem that was costing lives, understood its technical causes, and developed a solution using knowledge and resources available to him. His willingness to challenge official procedures and propose modifications demonstrated courage as well as technical skill, as unauthorized changes carried career risks. The success of his modifications proved that the risks were justified, and that operational necessity sometimes requires deviating from standardized procedures. If you found this story as compelling as we did, please take a moment to like this video, as it helps us share more forgotten stories from the Second World War. Subscribe to stay connected with these untold histories, because each one matters, and each one deserves to be remembered. And we'd love to hear from you, so leave a comment below telling us where you're watching from.